All right. So today we are going to talk about the theory of IR thermography. So IR thermography is particularly, important for measuring temperature, primarily temperature signatures in a non-intrusive fashion. That means, and it is also a field measurement. That means you don't need point measurements like what a thermocouple does, for example. So IR thermography is a little bit different from that. So again, we take a look at the electromagnetic spectrum. The electromagnetic spectrum is divided arbitrarily into a number of wavelengths and regions called the bands. All right. So these bands, if you look at it, they are distinguished into by their corresponding wavelength signature. Once again, this we covered already in multiple lectures, that the first one, for example, 1, which is about of the order of 10 nanometers, is where the X-ray lies. 2 is where the UV lies. 3 is the visible range, basically where we actually see, our human eyes can see. 4 is the IR range. So IR is subsequently divided into a few other parts, and this is the part that we are going to talk about. And then, of course, we go to the microwaves, which is 5, and then the radio waves, which is 6. So this is the full electromagnetic spectrum. Now, thermography makes use of the infrared spectral band. So at the short wavelength end, the boundary lies at the limit of visual perception. So where the visual perception ends, this particular thing actually starts. So at the long wavelength, it merges with the microwave audio. So it has got a very huge range, as you can talk about. So the infrared band is often subdivided into 4 smaller bands. So they are the near infrared, which is 0.75 to about 3 micron. This is right at the edge of the visual limit, so about to 3 microns. And then the middle infrared from 3 to 6 microns. The far infrared from 6 to 15 microns. And the extreme infrared from 15 to 100 microns. So you can see that it pretty much covers from 0.75 microns all the way up to 100 microns, which makes like 2 orders change in terms of wavelength. So it is a huge band, and you can see also that it extends over quite a bit of a region. All right. The 100 micron is roughly the size of a human hair, or the diameter of a human hair. So next we define what is called blackbody radiation. Now, what is a blackbody? I think from high school physics, you know that the blackbody is defined as an object which absorbs all the radiation that impinges on it at any wavelength. So it is an object which absorbs everything. Whatever wavelength that you hit it with, it will absorb. Then also you know about the Kirchhoff's law, which is named after Gustav Robert Kirchhoff in the 19th century, which states that a body capable of absorbing all radiation at any wavelength is equally capable of the emission of radiation at any wavelength. So this was Kirchhoff's law. So this is what the blackbody radiation is all about. So the construction of a blackbody source is also very simple. So how do you construct it? So the radiation characteristics of an aperture in an isotherm cavity, so which is made up of opaque absorbing materials, represents almost the perfect properties of a blackbody. So the practical application is a construction of a box that is light tight, except that you have a small aperture as one of the sides. So any radiation which enters this hole is scattered and absorbed within this by repeated reflections within this box, and only infinitesimal amount fraction can actually escape. So the blackness which is obtained at the aperture is nearly equal to the black body and almost perfect for all wavelengths. So this is how you normally construct. You construct a box with a small aperture. So by providing any isothermal cavity with a suitable heater, it also becomes what we call a cavity radiator. So if this isothermal cavity is equipped with a suitable heater, and you heat it to a uniform temperature, then it generates blackbody radiation. The characteristics is solely determined by the temperature of the cavity. So whatever is the temperature of the cavity, that determines the characteristics of the radiation. So these cavity radiators are very commonly used in radiation as temperature reference standards for calibrating thermographic equipments. For example, this provides a perfect, the temperature calibration device. So you can understand that this is raised to a particular temperature, and the characteristics of which is determined only by the temperature of the cavity. So this is how these things are constructed. So Max Planck in the early 20th century was able to describe the spectral distribution of radiation from a black body by means of this formula. So before this, there were a lot of attempts, but nobody could actually, model or provide a formula for the entire radiation that is emitting out of a black body. Planck was the first one to do that. Now, he also did it by pure luck to a certain extent, because this was more like a very complicated, intuitive guess, I should say. So if you look at it, you will find that there is a wavelength, that's the spectral distribution is actually scales as wavelength to the power of -5. And it has got obviously the h, which is the Planck's constant, k, which is called the Boltzmann constant, and c is the velocity of light. Okay, so the Planck's formula, we will see in the next page what it does. This now has a temperature. You can see the temperature is right there. So for various temperatures, it will produce families of curves if you look at it carefully. So for any particular curve, particular Planck curve, the spectral emittance is 0 at lambda equal to 0, and then increases rapidly to a maximum at some wavelength, and then passing it again, it goes to 0 at very long wavelengths. So this is how it actually functions. Okay, so when lambda is equal to 0, okay, lambda is equal to 0, the spectral emittance is also equal to 0, but then it peaks and then it goes to 0 once again at very long wavelengths. You can realize that it comes from the lambda to the power of -5 dependence. So this is how the the black body spectral radiant emittance according to Planck's law. This is plotted for various absolute temperatures. So these are the temperatures: 500, 600, 700, 800, and 900. Okay, and these are the corresponding wavelengths. So as you can see that the curves are mostly peaks at a particular wavelength. Okay, and this wavelength shifts to the higher wavelengths as we go on decreasing the temperature, but it gets pushed to the lower wavelengths when the temperature goes higher and higher. All right. So if you differentiate Planck's formula with respect to lambda, lambda, and you want to find out the maximum, you have the lambda max given as 2898 by T. So in other words, as the temperature grows, okay, the lambda max becomes smaller and smaller, which is exactly what you see over here. So 900 degree Kelvin is where the wavelength is very short compared to something at say 600. Okay, and this varies as 1 over T, as this particular formula shows. So this is called the Wien's formula, which expresses mathematically the common observations that colors vary from red to orange or yellow as the temperature of the thermal radiator increases, because that is the wavelength that we see. This is the wavelength at which the maximum spectral radiance actually occurs. So the wavelength of the color is the same as the wavelength of lambda max. This you got by now. So that's why we see this change in color from red to orange to yellow. A good approximation of lambda max for a given black body temperature is obtained by applying the rule of thumb, because this is 2898, difficult to calculate, about 3000 divided by T micrometer. So a very hot star such as Sirius, which is 11,000 Kelvin, emits bluish white light and radiates with a peak spectral radiance occurring somewhere in the invisible ultraviolet, which is the very low wavelength part, at around 0.27 micrometer, which is 270 nanometer. The sun, which is a much cooler star, at 6000 Kelvin emits light in the yellow and peaks about, say, 0.5 micron, which is in the middle of the visible light spectrum. All right. At room temperature, for example, which is 300 Kelvin, the peak radiant emittance lies around 9.7 micrometer, which is in the far infrared. Okay. So you can see why, measuring temperature at the infrared becomes an useful thing. Okay. Because you are trying to measure not objects like stars, but here you want to measure objects which are, around the room temperature or a little bit higher than that. Okay, while the temperature of liquid nitrogen is 77 Kelvin, and the maximum and almost insignificant amount of radiant emittance occurs at 38 micrometer, which is in the extreme infrared wavelength. Also remember that this peak actually comes down drastically. So 300 Kelvin will be somewhere below 500, and 77 Kelvin will be minuscule. So it is not just the maximum wavelength, it is also the intensity that varies quite a bit. Okay, so this is just one criteria, but the radiant emittance is quite low, but it lies in the extreme infrared wavelength. So lower the temperature, higher the wavelength. Essentially, that is what higher the maximum wavelength. So, if you plot this, so this goes up to about 100 Kelvin. So liquid nitrogen is even lower than this. So that's why we get around 38. So the Planckian curves plotted on a semi-log plots from 100 to 1000 Kelvin. So this is 1000, this is 100. And the dotted line represents kind of the locus of the lambda max. So, represents the locus of the maximum radiant emittance at each temperature as described by the Wien's displacement law. So the spectral radiant emittance, so this is the spectral radiant emittance and this is the wavelength. So this is how the curves are basically plotted. So this is the locus of the peak as it shifts. So we are making a case that why infrared is important. So if you integrate Planck's formula all the way from 0 to infinity in the wavelength space, we obtain the total radiant emittance of a black body, which is given as sigma t to the power of 4. This is the Stephan-Boltzmann formula, named after Joseph Stephan and Ludwig Boltzmann. Ludwig Boltzmann was a pioneer of statistical mechanics, which states that the total emissive power of a black body is proportional to the fourth power of its absolute temperature. So at very low temperature, this will be low. As you go on increasing the temperature, this increases drastically because of the fourth power dependence. So generally, this represents the area below a Planck's curve for a particular temperature. So if you look at this particular curve, so this will be the entire area under this curve. So you choose any one curve, the area under the curve basically gives you WB, which is the total radiant emittance. Okay, so it can be shown that the radiant emittance in the interval 0 to lambda max is only 25% of the total, which represents the amount of sun's radiation that lies within the visible spectrum. So, okay, so it is only 25% because the curve, if you look at it, has got a long tail. So if you look at it, the curve, it has got a long tail. Okay, the tail portion is quite long. It's not symmetric at all. Okay, so that is what you get. Okay, and using Stephan-Boltzmann formula, okay, to calculate the power radiated by the human body at a temperature of say 300 Kelvin, we are roughly around that temperature, and at external surface of about 2 meters square, we obtain about 1 kilowatt. This is the power that is radiated by a human body. So that is what it is. So it comes from the Stephan-Boltzmann law. Okay, so non-blackbody emitters. So far we have considered only blackbody radiators and blackbody radiation, but however, real objects almost never comply with these laws over an extended wavelength region. Also, they may approach the blackbody behavior in certain spectral intervals. For example, when a certain type of white paint may appear perfectly white in the visible light, but becomes distinctly gray at about 2 micron and about 3 micron, it is almost black. Okay, so there are three processes which occur that prevent a real object from acting like a black body. So a fraction of the radiation alpha may be absorbed by the body. Okay, a fraction rho may be actually reflected, and a fraction t, a tau, may be actually transmitted. So since all these factors are more or less wavelength dependent, there we use a subscript lambda to imply that there is a spectral dependence for their definitions. So for example, the spectral absorptance, which is alpha lambda, is the ratio of the spectral power absorbed by a body to the total power that is incident on the body. Similarly, spectral reflectance, which is rho lambda, is a ratio of the spectral radiant power reflected by an object to that of incident upon it. The spectral transmittance, which is tau lambda, is the ratio of the spectral radiant power which is transmitted through an object to that incident upon it. So you can see, if you sum total of all these three terms, because they all have the total power at the denominator, okay, this is going to be 1, okay, because we have accounted for all the energy essentially. For opaque materials, the transmittance is 0, so the relation simplifies to there is an absorptance and then there is a reflectance. So the sum total of these two should be equal to 1 at any particular wavelength, for example. Okay, so the emissivity is a ratio of the total spectral radiant power emitted by a body to that of a black body at the same temperature and wavelength. So the black body is like a reference. The black body which is at the same temperature and same wavelength, if you put it in the denominator, so the emissivity is the ratio of the spectral radiant power emitted by an object, any object, compared to a black body. Essentially, that's what it is. Okay, so lambda b actually designates a black body and this designates any object. So generally speaking, there are three types of radiation source distinguished by the ways in which the spectral emittance of each varies with wavelength. A black body for which this is equal to 1, so the emissivity is equal to 1 at any given wavelength. A gray body for which this is a constant, the emissivity is a constant, but it is less than 1. And a selective radiator in which this is now a function of wavelength. In a gray body, we do not have a wavelength dependence. It is a constant across all wavelengths, but it is consistently a factor which is below a black body. A selective radiator, on the other hand, it emits at certain wavelengths, but that varies, with the wavelength that you are concerned with. So many of the the missiles and other things, they have selective radiators as well. Okay. According to Kirchhoff's law, for any material, the spectral emissivity and the spectral absorptance are equal at any specified temperature and wavelength, which means that emissivity E lambda is equal to alpha lambda. So for highly polished material, this approaches 0. Okay, so that for a reflecting material, we have rho lambda is equal to 1. Okay, like a mirror. A mirror is always reflecting. Okay, so this is almost equal to 1. So these are the stories of the black body emitters. So far, only black body emitters. So okay, in the wrong way. So let us see for a gray body radiator. Okay, the Stephen-Boltzmann formula, therefore, just is revised. You have this coefficient, epsilon, which just sits on it, which is the emissivity. So this states that the total emissive power of a gray body is the same as a black body at the same temperature, reduced by a proportionality, reduced by a scaling factor, which is epsilon. So This is, for example, a typical graph. So this is the spectral, again, this axis is the spectral radiant emittance, and 2 is the wavelength. 3 is actually a perfect black body. 4 is a selective radiator. So you can see it has got a very weird shaped curve. That means that it has got selective, at certain wavelengths it emits, at certain wavelength its emission is decreased. And 5 is like a gray body, where everywhere there is a scaling factor which offsets it from a true black body. So this is how this is actually working. Okay. So how do you do a measurement of this? So when you view an object, the camera receives radiation not only from the object itself, but it also collects radiation from the surroundings reflected via the object surface, right? So when you are actually looking at an object with a camera, so this is an object of interest, this 2, okay? And this is the surroundings, which is basically 3, which is atmosphere, and 4 is your camera, right? Okay, and 1 is the surroundings, 3 is the atmosphere, 4 is the camera. So when you view an object, the camera receives not only the radiation from the object itself, but it also collects radiation from the surroundings reflected via the object surface. So both these radiations becomes attenuated to some extent by the atmosphere, because atmosphere is in the measurement path, so it should absorb, it should also behave in the same way as a media. So to this there comes a third radiation contribution from the atmosphere itself, therefore. Okay. So what has been neglected, for instance, will be sunlight scattering in the atmosphere or stray radiation from outside the field of view. So these disturbances are difficult to quantify, but in most cases you should do the measurement in a setting where these things are minimal. Okay, so as you can see, this is the temperature of the object which we are interested in, because that is what we want to measure. Okay, this temperature can have a spatial variation as well. So now you have the atmosphere and you have this very complicated, budget. Okay, so part of it is actually part of the radiation that is incident is actually emitted. A part of it is actually reflected. All right. So here also you can see now it passes through the atmosphere. So it has got a transmittance of the atmosphere, which is multiplied to this emissive power. And then you actually have a reflected part in the same way. And then the atmosphere also contributes something to the camera. So the camera receives radiation from basically 3 sources. One is from the object, which is emitted, plus part of it is lost during transmission through the atmosphere. So it receives an attenuated radiation. And then it receives also some reflected radiation, because that also passes through this medium, again gets attenuated and reaches the camera. Then the atmosphere itself actually contributes to a great extent, because it also can radiate, and it contributes from the atmosphere. So we are neglecting sunlight, stray light, any other radiation sources that can be there in the vicinity. All right. So this is it collects radiation from all the possible objects. Now, if you assume that the received radiation power W from a black body source of temperature T source on short distance generates a camera output signal U source that is proportional to the power input. Okay, so this is like a power linear camera. Okay, so the U source is actually equal to C into W source. So it generates a input, a camera signal, which is proportional to the input power. Now, should the source be a gray body with emittance epsilon, the received radiation would consequently be a EW source, right? Because this is for a black body. If you replace it by a gray body, we know that this will be just epsilon. All right. So the camera responds to the incident radiation or the radiation power from a black body in a linear fashion. Okay, so whatever power it receives from the source, okay, it is multiplied by a proportionality constant, and it is reflected in the U source, which is the signal that is generated by the camera. Now, this W source, when it becomes a gray body with emittance epsilon, right, the received radiation would consequently be, epsilon into W source, right? So this is an important, the argument that this is a power linear kind of a camera. Okay, so more is the source, more is the signal that is actually generated in the camera. Okay, so just to take just to make sure that you understand that what we did in this particular class, we kind of knew about the black body, then we knew about the different non-black body emitters, then we talked about the Stephan-Boltzmann law, and then we talked about the Planck's curves, right? We talked about what are the selective radiators, what they will be, okay? And we also saw examples of the selected radiators. And then we saw that when you try to measure the temperature of an object using this camera, which is like an IR camera, for example, so it basically collects radiation from a lot of sources. And we described what these factors are all about. And once that is done, then we saw that if the camera is linear, our linear camera, then it should respond to that incident radiation power or radiation power in a linear fashion. So we will stop at this particular moment for this particular class, and then the next class we are supposed to complete the IR thermography.